thank you. It's a great pleasure to be here. I'd like to thank the organizers for setting up this wonderful workshop and giving me the chance to present. So I'm also going to be talking about bismuth, but in a very different regime, and not the bismuth edge states, but surface states, and looking at novel interaction-driven phenomena that can occur in the quantum Hall regime here. And so what I'm going to talk about are these nematic quantum Hall states. So we'll discuss what they are and how we identify them by directly imaging the underlying wave functions. And then the second half of my talk will focus on looking at boundaries between different nematic regions where we see some very cool interaction effects that occur. So just briefly, nematic electronic states are states that break the rotational symmetry of the underlying crystal lattice. And these are analogous to classical liquid crystal phases. And these nematic states were first proposed and inspired by the observation of stripe phases in high-temperature superconductors. They've also been studied extensively in a number of material systems, including, you might have heard of gallium arsenide around μ=9/2, or strontium ruthenate experiments. And the signatures of these experimentally is that the electronic behavior along different crystallographic axes is dramatically different. So the electronic states themselves have a certain preferred directionality or orientation to them. But the key question for these nematic states is, do they form spontaneously? That is, as a result of electron-electron interactions. And so now I'm going to talk about, for the most part, a different platform in the quantum Hall regime where interactions are known to drive different kinds of symmetry breaking. And so the quantum Hall regime needs no introduction to the people here, but essentially the idea is you have a two-dimensional electron gas in a large magnetic field, and the kinetic energy of these states gets quenched, so you have these Landau levels with large degeneracy, and this is what allows Coulomb interactions to dominate. And so in systems that have several degrees of freedom, that could be either from a spin degeneracy or some pseudo-spin coming from Valley or Lair degrees of freedom, this adds an additional degeneracy to the Landau levels. And so when a Landau level is then partially filled, what can occur is this quantum Hall ferromagnetism behavior, as it's called, but essentially Coulomb interactions make it energetically favorable to lift one of these degrees of freedom and lift that degeneracy and open up this gap, this exchange splitting right around the Fermi level. And so this is purely an interaction-driven gap that occurs only when the Landau level is partially filled. And so these kinds of this kind of behavior has been studied in many different systems, including graphene, primarily using edge mode transport. And in graphene, you have some SU4 symmetry from spin and Valley, and there are all kinds of exotic phases that have been proposed. And experimentally, the studies typically use these edge modes to look at transport and lifting of these different degrees of freedom. But here, what I'm going to talk about is, again, using STM and local probes to directly be able to image the wave functions and also look microscopically at what's happening in the system. And so now to bring in nematicity and this idea of some anisotropy into the system, we consider a case which has a Fermi surface that looks like this, which has multiple valleys that are anisotropic. So here you can see this schematic has two valleys colored in red and blue that are elliptical. And what this means is if we can now tune this system into the regime where we have this exchange splitting between these two different degenerate valleys, then the real space cyclotron orbits should also reflect this valley anisotropy and have a certain directionality to them that breaks the fourfold rotational symmetry of your entire system here. So this kind of anisotropic multi-valley system can form a model nematic system where we can study, first of all, the breaking of the complete rotational symmetry by looking at the shape of the cyclotron orbits here, and also directly quantify the role of interactions by looking for these energy gaps around the Fermi level. And now in these systems, we also expect to have domains, and a lot of transport measurements typically use some small polarizing field to be able to study macroscopic behavior along that like picks one direction to see this anisotropy here. But in this case, by using local probes, we can really try to look for different regions with different domains, and furthermore study boundaries between different nematic regions. And these boundaries themselves are interesting in their own right because we expect the boundaries to host one-dimensional modes that are valley polarized, just coming from the edge modes of your quantum Hall system. But here, this one-dimensional boundary is now a very clean system in which we can ask what kinds of interactions do we see at this one-dimensional boundary, and studied with the local probe, do we see some behavior, some Luttinger liquid physics emerge, and specifically in these valley systems, how does the valley degree of freedom influence these interactions? And so I guess the overview of my talk is just going to be discussing, first of all, how we can tune the bismuth surface into this kind of quantum Hall regime and show you that we see nematic behavior and spontaneous valley ordering in these systems, and we can directly image the underlying Landau level wave functions using an STM. And then finally, I'll show you how we are able to find a very pristine nematic domain wall and a boundary here where we see some cool interaction effects. So STM, I guess Barrett gave a great introduction to what STM is. And we have the same pictures coming from the same group. So, right, so STM, in addition to having this beautiful atomic resolution imaging, it's a very versatile probe that can be used for spectroscopy. And so we use it both to obtain information of the local density of states. So I'll be showing you data which looks like this, where we show tunneling conductance as a function of bias voltage between the tip and the sample, or energy. And this is just the local density of states at one point over a certain energy range. We can also perform spectroscopic mapping, where we fix the energy and look at how this tunneling conductance, dIdV, varies over a certain area of our sample. These are the kinds of measurements that I'll be showing you. And the STM that we use for the experiments here goes down to 250 millikelvin electron temperature and has magnetic fields up to 14 Tesla. So this allows us to access this high magnetic field regime. So what we do in our system is we just cleave a single crystal of bismuth and expose the 111 surface. These are not the thin films, but this is just a cleaved crystal. And we're looking now primarily at the surface states, far away from any edges. The band structure of this material has been long studied and is very well known, both theoretically and from ARPA's measurements. This material has large spin orbit coupling, which lifts the spin degree of freedom and gives you these two spin split surface state bands shown in yellow and blue here. So there's no spin degeneracy, but the Fermi surface schematically looks like this, and it has these multiple valleys or pockets. And I'm primarily going to focus on the pockets that come from this blue band here. These are these 6 anisotropic valleys labeled as whole valleys based on this band here. And you can see these valleys should remind you of the model nematic system that I was talking about, some anisotropic valleys. But there are also other pockets coming from some of these other bands in the material. And if you look here, right, the bismuth lattice has some threefold rotational symmetry. And so now what we do is we can measure the system at 0 magnetic field. We get some smooth curve that looks like this in our tunneling conductance. And now when we turn on a large magnetic field at 14 Tesla, our spectrum shows these very sharp peaks here. And these peaks are directly correspond to Landau levels in the system. Now we can, in order to understand these Landau levels better, we can look at how they evolve as a function of magnetic field and track their dispersion. So plotted on the bottom here is a fan diagram where we have magnetic field as a function of energy. And if you look closely, we can see there are 2 types of states, one that disperse very strong states that you can see here. These are coming from the 6-fold degenerate whole valleys that I was talking about. And we also see some Landau levels dispersing with the opposite slope coming from these peaks here, from the central electron Landau level. But most importantly, we can identify the n equals 0 Landau level here that corresponds to essentially the energy of the top of this band here, and we see it very clearly in such an evolution. And so without going into too much detail behind this now, I just want to say that we can identify which Landau level we're looking at, and also in this material and in this system, we can tune the magnetic field to change the filling factor of these Landau levels. And there are some technical details behind this which I'm happy to discuss later, but that's what's to remember here. So now if we zoom in on just one of these Landau levels, which has the 6-fold valley degeneracy, we zoom in around the one that's close to 0 energy because we want to try to look for some splittings and liftings of degeneracy. And so to orient you here, I'm focusing on this Landau level here. This is this hole-like Landau level, and we see that what was previously showing up as just one peak is actually split into 2 peaks here, and it's actually split into a 2-fold and a 4-fold degenerate state. So the 6-fold valley degeneracy is lifted, and I'll convince you of the degeneracies of these split peaks in a couple slides. So this splitting here is some single particle splitting that we see in our system that's independent of where the Fermi level is, where E equals 0 is, and independent of orbital index. So it's likely from some strain in the sample. But now we can further tune the magnetic field. And at this magnetic field here, you see if you look at the individual spectrum, that 4-fold degenerate state further split. And this is due to this exchange interaction that I was talking about, where when this level is partially filled, it splits due to Coulomb interactions. And this splitting only occurs around the Fermi level. And if you look at this energy scale here, this is looking with very high energy resolution at a plus minus 3 milli-electron volt energy range. And this exchange splitting, the Coulomb's interaction is on the order of 500 microelectron volts here. So what we can see is we can tune the magnetic field to a regime where we've lifted the 6-fold valley degeneracy into 3 doubly degenerate states here, where we see 3 split peaks. And now in order to try to understand further what's the nature of this symmetry breaking, what we can do is look at conductance maps at the energies of each of these 3 split peaks. And so this is one conductance map shown here at the energy of this lowest split Landau level. And what you see is this is now taken over a certain area of our sample just at one energy, mapping variations of this tunneling conductance. And you can see these ellipses with a long axis oriented vertically. Now, if we take measurements in the same area of the sample, but at these different energies of the other peaks here, we can see that these ellipses now are diagonally rotated with 120 degrees with respect to one another at each of these 3 energies. And so this is, so these ellipses are, they're images of individual Landau level wave functions that are centered on defects. But the idea is essentially you can see the ellipses break the 3-fold rotational symmetry of your underlying system. We have these, at the different energies, the electronic behavior has some different orientation to it. So this is this manifestation of nematicity that I was talking about. And what these ellipses are is that they're actually individual Landau level wave functions pinned to defects that I don't have time to go into how we know precisely what they are, but I'll show you a zoom in just around one of these ellipses here. So this is an image of just one of these individual ellipses, which is an individual Landau orbit. And what you can see is there are actually several rings that correspond to the different nodes in the wave function. And it matches very well to a simulation for the n equals 3 Landau level, where the only free parameter here is the ellipticity of it that comes from the ratio of the effective masses in the Fermi surface itself. And this value matches well to what's expected for the Bismuth Fermi surface as measured with ARPAs and other experiments. So up to now, what we've been able to do is In the absence of any symmetry breaking, if we have a Fermi surface in momentum space that has these 6 pockets, then we expect the real space Landau level wave functions to have ellipses with these 3 directionalities superimposed upon one another. And this is now not breaking any of the rotational symmetries of your underlying lattice. But if we can lift the 6-fold Valley degeneracy, what we were seeing was ellipses pointed along 3 different directions. These are just coming from pairs of valleys at opposite momenta. And this valley anisotropy is directly reflected in the ellipses and the conductance maps that we were seeing in the wave functions. So this is the data I was showing you earlier, where we can image these 3 different broken symmetry states. Now if we tune the magnetic field, we can close this exchange gap between the 2 states here, and we can move to a state that's 4-fold degenerate, and then the conductance map taken at the same area as these top 3 measurements, just at a different magnetic field, now shows ellipses with both directions superimposed. So this is a direct manifestation both of this nematicity and a case where we can quantify the role of interactions in this material, or in this system. And now what we can do is say, okay, we see this,
Can I ask
Yes.
about, so here the splitting between the 4-fold and the 2-fold peak,
Yeah.
you said comes from strain and is independent of interaction.
Yeah.
So the breaking of rotational symmetry is not spontaneous, it's
In
extrinsic.
between this and this is not spontaneous. There's some single particle effect. Yeah, but between these 2, like the 4-fold splitting into 2 2-fold states, that's the spontaneous case.
Right. I guess it's some other further symmetry that you're breaking in that case. Rotation symmetry is already broken.
So I guess the way to think about it is what we're actually doing, the valleys themselves have some anisotropy, but is that your question? Sorry, I didn't quite understand your question.
If you say strain is breaking rotational symmetry, to make this splitting, the states that remain are already broken. I mean, rotational symmetry is already broken. There's maybe some mirror symmetry that's related in the other 2. That's the one that's been broken spontaneously. Yes.
Yeah, so in this case it would be,
Some symmetry that relates these 2.
Yeah. But the idea is that interactions, well, we can quantify which symmetries are being broken by interactions as opposed to single particle effects.
Yeah.
Because we can do measurements like this and really compare these 2 cases. Yeah. And this symmetry breaking is from interactions. But let's discuss more. There are some nuances about the strain and interactions and how they have some interplay. So
One short other question. Is there an intuition why at higher field these 2 peaks merge and at lower field they split?
So essentially, if you're tuning the filling, if all 4 states are unfilled, it's 4-fold degenerate. You fill them, fill it partially, they split, and then you can keep going in field and they should close again. Yeah, that's a good question. Right, so now we want to say, okay, we can look locally at these different nematic regions. Can we find a boundary between them? And what was quite exciting for us is we were able to find in a very clean, large area of our sample. So this is just a surface that's completely featureless in topography. But if we look electronically at the conductance maps, we see this very striking domain wall here. So here we have these Landau level wave functions pointed in different directions on the left and right, and across, cutting through the middle, is this electronic domain boundary. So this is not a structural domain boundary. It's electronically, we see it just in the conductance maps when we take an image at one of these Landau level states. And so what we expect to say is, okay, if one side we're occupying one valley and on the other side we're occupying a different valley, then we should have these one-dimensional modes that are valley polarized and counter.
Please, may I have your attention, please? This is the Fire Life Safety Director. We are conducting a test of the fire alarm system. Please disregard all alarms. I repeat, we are conducting a test of the fire alarm system. Please disregard all alarms.
Okay, great. So now to study this crossing, what we can do is take a line cut going from one domain into the other domain, and what we see is this exchange gap between two doubly degenerate states here. So individual spectra are these two peaks that I was showing you, split by exchange around the Fermi energy. This exchange gap closes and reopens here. And what's occurring is essentially which valley states are occupied on each side is switching. So you can think of this in some hand wavy term as some topological gap twist where there's some valley churn number that's changing. And this is what should give rise to these one-dimensional modes here. What we can see with STM is if we take conductance image at E equals 0 at this crossing point, the boundary lights up and it's very bright because it has high conductance. Now what's particularly unique about our system is that we can tune between two different cases, a case where we have one set of counterpropagating modes or a case where we have two sets of counterpropagating modes. So now we're considering this subspace between the four valleys that were degenerate without any interaction. So I'm calling them A and A bar, one pair of valleys, and then B and B bar. So we can either have some effective filling factor nu tilde equals 1, where it's just one set of counterpropagating modes, one valley occupation that's switching as you go from one domain to the other, or two sets of counterpropagating modes where A and A bar are occupied on one side and B bar on the other side. And the way we do this again is just by tuning magnetic field, and we can really tune between a case where that fourfold degenerate peak is either split into a singly degenerate state and a threefold degenerate state or two doubly degenerate states here. And again, if we look at some line cut, we can similarly see that this exchange gap between them closes right at the boundary. But now we can ask, okay, to study the boundary more carefully, can we look at the behavior right at the domain wall? And here's where we see something that was quite surprising initially. So if we look at a spectrum taken right at this crossing point, right at the domain wall, in the case where there's one set of counterpropagating modes, this mu tilde equals 1, this mode is gapless, it's a metallic state, that's what we would expect. But in the case of mu equals 2, anywhere along this crossing point, if we look at an individual spectrum, shown in green here, there's always a residual gap. This is what I'm calling this charge gap here. So these states are actually gapped. And we see a very striking difference in behavior between these two states at the boundary. And naively, you could say, oh, maybe there's some disorder in the system which is gapping out these modes. But both of these measurements are done in the same area of the sample, just a different magnetic field. So the disorder profile is completely the same. So it's not so any disorder that would gap one of these modes should also affect the other mode, should also affect the system in either case. So instead, what we need to do is now consider interactions between these different modes and think about whether there is some interaction process that could gap out modes in only one of these two cases. So first, if we just look at the case where we have one set of counterpropagating modes at the domain boundary, here some interaction which takes A to B but B back to A. This is some gapless process. And so it would just keep the states gapless as we see. We could also expect some kind of effective backscattering type of process where we have states in valley A going to valley B just as some interaction. But this, if we look at what this interaction involves in terms of momentum transfer in the 2D Brillouin zone, because we're really considering states that are coming from valleys at different momenta, this kind of large momentum transfer would be exponentially suppressed. So these kinds of interactions are exponentially suppressed in this case. And so that's why this state remains gapless. Now, in the case where we have two sets of counterpropagating modes, there can be interactions in this case that look like taking valley A to B and A bar to B bar. This is some kind of effective backscattering type of interaction, but if we look at now this case, the momentum transfer in the 2D Brillouin zone, these states have net zero momentum transfer because it's two sets that cancel out. And so this is the type of interaction processes that aren't suppressed to this degree and can gap out the modes here. And these are precisely the kinds of interactions that open up this charge gap, only for the case where you have two sets of different, two flavors of value modes going in each direction. Then there are also processes, how much time do I have? That's okay, I'm basically done. Okay, yeah. Okay. There are also other processes that, in this case, would also be exponential.
May I have your attention, please? May I have your attention, please? This is the Building Fire Life Safety Director. We have concluded our testing of the fire alarm system. All systems are normal. Repeat. We have concluded our testing of the fire alarm system. Thank you.
Great. Well, I'm almost done too. This is really the key point of the second half of the talk, though, is that we have a unique system where by being able to tune the number of modes that we have at this domain boundary, we can really change the interactions between them and go between a case where we have a metallic gapless mode at the boundary and a case where the modes that we can measure are gapped. And these interactions are different from something you would expect in a purely 1D system because we really have to consider the momentum transfer involved in the 2D Brillouin zone. And so that's really the takeaway message here. We can also understand these theoretically from a Luttinger liquid point of view, and we were working with purists to develop that framework as well, which I'll point you to this theory paper here. And with that, I'll just end by saying, I hope I've convinced you, taken you on a different journey of business, in this case the surface states, where we were able to look at spontaneous Valley ordering that occurs in these systems and also directly image the Landau level wave functions in these systems, and then look at these nematic domain walls and study their interactions. I think there's a lot more to do on that front in Bismuth specifically, to look at domain walls between the three different directionalities that exist and study these kinds of Y junctions. But more generically, these anisotropic Valley systems can apply to many different materials, and so it would be interesting to expand it further, looking at either domain boundaries or just other effects. And in terms of the imaging side of things, possibly expanding the imaging of Landau level wave functions to either the fractional quantum Hall regime or to other excitations like fermions that produces these systems. Yeah, and with that, I'd like to thank all my collaborators. This work was done in Ali Yazdani's group at Princeton during my PhD. I worked primarily with Ben Feldman, who's now at Stanford, and Andras Ginish and Hao Ding, who's still a postdoc with Ali. The samples were grown by Bob Kava, and we had great theoretical support from a number of different people, Feng-Cheng Wu and Alan McDonald initially, and then Karthik, Sid, and Shivaji on the Luttinger liquid understanding of these domain walls. So yeah, with that, I'm happy to take questions. Yes?
Do you see other domain walls with different orientations? Because the direction of your domain wall is a bit strange. I mean, it's orthogonal to one of your value, but has a different angles to the other value.
Yeah.
And usually, the domain wall orientation, they usually have some, energetic preference along a certain direction, and they should be
right. So that's a very good question of like what's setting the direction of this domain wall. It's kind of you have to take into account the entire energetics of the system, and this was what we found naturally. We have not, so it's hard experimentally, very difficult to find these kind of pristine domain walls, so we have not been able to study a completely different second domain wall. The reason being that typically when we cleave our crystal surface, there are many step edges, and so you see different nematic domains, but the crossing point between them can sometimes be obscured by some topographic steps in your sample. But yeah, I think in terms of understanding the direction of this particular domain wall, this is just the way it was at this particular location of the sample.
Does the direction matters for your scattering and then this protection at the end of your talk you're talking about?
Oh, that's a good question. To first order, no, but I think I don't know, we should talk more about it, maybe, yeah. There could be so one thing we did think about was if you have the different orientations, like it's not, if you project the valleys onto the domain wall, there could be some charge polarization which shows up, some dipole moment, because the projections won't perfectly cancel out, because like you're saying, you notice the domain wall doesn't perfectly bisect the two angles. Right. So there is something with that.
One more question then about the strain. So if you look at the peak that was split by strain, the orientation of this peak, is it homogeneous throughout the sample, or does it also change?
No, that also can change.
That can also change.
Yeah, yeah. So locally it's a certain orientation, but if you go, so our images were around 200 by 200 nanometers. If you go like a micron away, that can also change.
The splitting in energy between the purple and the purple, is it the same?
That can also change depending on the magnitude of the strain.
Right.
So I guess that's really what the STM was very good for, is identifying locally what is the magnitude of the strain, and then by imaging, identifying the orientation of the wave functions associated with that particular peak, and looking locally at these differences. Yeah, but I'm happy to talk about energy scales more as well.
Yeah, kind of a similar question. So you could also imagine a strain which splits all of them into 2, 2, 2. Do you also see that?
We do also see that. But, right, we also see that. The case where strain cannot lift any degeneracies is now this twofold state can further split into one.
Oh, yeah, okay.
So because I showed the 1 and the 3, where we had one set of counterpropagating modes, that 1 can only be split by interactions. Because if you look at the way the valleys are oriented, strain will always at least pick 2.
Yeah.
Yeah, we've done some mapping of strain profiles and things. Yeah.
When you consider like future experiments, could you imagine like sweeping the field up and down through those fillings and domains to see if nematic, these domains kind of change their location? If it's fully nematic, there wouldn't be any reason for the domain wall to stay in one position, right?
Right. So in our case, we did that with this domain wall. It is hinged to where it is, and there is likely some strain and underlying energetics that is fixing it where it is. So although the splitting is spontaneous, like we can tune to a regime where we see no nematic domain wall because the two peaks with the two orientations are not split in energy. But in terms of going back, when we go back to a regime where there is exchange splitting, it always picks the same direction on the same side. So there is some underlying single, I guess, like strain that's favoring one direction or the other.
Right.
And picks the lower energy state when you split it.
Yeah, so related to that question, when you change the filling, do you see the gap of 2, 2, close and then reopen for and then
into the 1?
Yeah, into the 1, and then maybe you can even map the phase diagram as a function of filling.
How about we talk later? I can actually show you exactly that data where we have a fourfold state splitting into 1 and 3, and then that gap closing and splitting into 2 and 2, and then going on. Yeah, that's a great question.
Righty. Last one.
Entree.
What's the lowest field that you see the nematic behavior for?
So that's a very good. The lowest we've seen the nematic behavior we measured around was 10 Tesla. But we see the Landau levels showing up already at 4 or 5 Tesla. The question is at what, given our energy resolution, maybe like 8 Tesla is where we could see significant splitting. So the splitting is on the order of 500 micro eV.
So there's no chance of adding a superconductor?
Well, no, that's actually a very interesting question. We should talk about that. It depends on what the HC2 of the superconductor is, but you can have some that survive.
Out of plane?
Yeah, this is out of plane. You could have vortices.
Yeah.
but 8 Tesla, maybe 5 Tesla. I think, I mean, it would just be, I'd have to look at which Landau level we're in and what the magnitude of the splitting is to see if it's resolvable. We have about 100 micro EV energy resolution in our system. So that's what's limiting us.
Great. So
Okay.
thanks again.
Thank you.